Hello, welcome. In this short video, let us analyze the even and odd nature of a sinusoid on the phase of the signal. So we are going to look at dependence of even or odd nature of sinusoids on the phase term. Given the signal x of t equal to a times cos of omega t plus phi, that is a classical sinusoidal signal. A is the amplitude, omega is the frequency, phi is the phase. So the even or odd nature of this signal depends on the value of phi. So for example, in the first case, if phi is equal to a multiple of pi, that is n into pi, phi is a integer multiple of pi, then x of t is always even. You can easily verify this one. X of t is equal to a times cos of omega t plus n pi. Since cos of a plus b is cos a cos b minus sin a sin b, the second component, that is a times cos of omega t into cos of n pi, and then we have minus sin of omega t sin of n pi, and sin of n pi is always 0. So x of t reduces to a times cos n pi is basically minus 1 power n and then cos of omega. So this function is always even. So x of t is even whenever phi is equal to n pi. We can easily verify this one. We can easily verify this one in MATLAB. Phi is a phase term, is basically a multiple of pi, in this case 1 into pi. So what happens is the signal is exactly even. That is, there is a signal plot t comma xt, which is the original signal, and plot minus t comma xt, which is the time reversal signal in the red. So they actually match each other perfectly. That means it is an even signal. And we can verify the same thing for all the any multiple of pi. So for example 3 pi. Again we can clearly see that x of t is even. Now let us look at the odd nature, that is when the phase term phi is equal to an odd multiple 2n plus 1 into pi by 2. In this case, x of t will be an odd function or odd signal. Let us verify the claim. X of t is equal to a times cos of omega t plus 2n plus 1 into pi by 2. So in this case, what happens is this cos of a plus b, the first term becomes 0, that is a times cos of 2n plus 1 into pi by 2, which is always 0, and then cos of omega t, so it doesn't really matter, so it's still 0, and minus sine of 2n plus 1 into pi by 2 multiplied by sine of omega t. So depending on the value of this function, it is usually minus 1 or plus 1. So x of t is, irrespective of the value of sine of 2n plus 1 pi by 2, sine of omega t is always odd. So when you multiply a constant to this odd signal, you still get an odd value. So x of odd or an odd function, so x of t is basically minus a sine of 2n plus 1 into pi by 2, that is sine of 2n plus 1 pi by 2 multiplied by sine of omega t. So this is always an odd signal because everything else is basically a constant, so it's an odd signal. So whenever the phase term is equal to an odd multiple of pi by 2, x of t is an odd signal. Clearly x of t is not equal to x of minus t. However, it is equal to minus of x of minus t. That means the signal x of t matches minus of x of minus t. That is, it is an odd signal. And finally, in case 3, when phi is not equal to an integer, when phi is not equal to a multiple of pi by 2, that is phi is not equal to n times pi by 2, where n is an integer. In that case, that is, say for example phi is equal to pi by 3, then in that case the function x of t is neither even nor odd. That is, it is neither even nor odd. So in this case, phi is equal to a number or a value that is not equal to a multiple of pi by 2. In that case, x of t is neither even nor odd. So we can easily verify again by taking a value for phase, suppose for example pi by 4, which is basically not a multiple of pi by 2. So it should be, you can easily see that x of t and minus of x of minus t is not equal, and also x of t is not equal to x of minus t. So therefore the signal is not equal to x of minus t or minus of x of minus t. That means it is neither even nor odd. In other words, if the cosine signal has a phase term and the phase term is not equal to a multiple of pi by 2, then both the terms actually contribute to the signal. So that means it's a combination of an even and an odd signal. So and the combination is obviously not either even, it is not either even or odd. That is, it is neither even nor odd. So to summarize, in this video we have looked at the dependence of the even or odd nature of sinusoids on the phase term. That is, given x of t is equal to a times cos of omega t plus phi, for 3 different types of values of phase, the x of t has 3 different natures. For example, when phi is equal to, that is phase is equal to an integer multiple of pi, then x of t is purely even. That means the cos of omega t plus n pi omega, that it basically simplifies to cos of omega t multiplied by a constant. And similarly, for phi is equal to an odd multiple of pi by 2, that is phi is equal to 2n plus 1 into pi by 2, x of t simplifies to a constant multiplied by sine of omega t, that is, it is always an odd signal. And finally, for a phase value that is not equal to a multiple of pi by 2, it is neither n pi nor 2n plus 1 into pi by 2, in that case x of t is found to be neither even nor odd. And we have verified the same using MATLAB. That is, for example, by taking a multiple of pi, the signal is equal to its reflection. So our x of t is equal to x of minus t. And when it is a multiple of pi by 2, that is an odd multiple of pi by 2, in that case x of t is equal to minus of x of minus t. So that is an odd signal. And finally, for phase term equal to something is not equal to a multiple of pi by 2, in that case it is neither even nor odd. Thanks for watching.